former students.
Yeah, just 2, I think. Yeah. See you. Okay, hi everyone. So today we're gonna talk about oxidation reduction reactions a little bit more. So what I told you last time is that oxidation means electrons are removed, reduction means electrons are added, right? And oxidation means we have a decrease of the oxidation number. Okay, so oxidation means electrons are removed, which means that the oxidation number increases, and while reduction is exactly inverse, right? Reduction means electrons are added, which means that oxidation number decreases. Okay, so this is the basic idea. The oxidation number, as we said, for ionic compounds will usually just be the charge. And for covalent bonds, we will assign the electrons based on the electron affinity. So some element which wants to take the electrons more than the other will just get all the electrons from the bond, right? That's the idea behind it. So it's kind of the extreme case of the battle for the electrons, right? The one who wants them more will just get all of them, right? And then once we have these numbers, then we realize that many of the chemical reactions are oxidation reduction reactions. We did various examples for this. And in the end of that lecture, we realized that we can usually split that oxidation reduction reaction into the half reaction, one for the oxidation process, one for the reduction. And that helps us to balance these equations a little bit, because it can be a bit tricky sometimes to balance them. By splitting them, we will introduce explicit electrons into the chemical equation. And then we have to just make sure that the electrons are the same. So let's do some example for that today. We start with a potassium dichromate, K2Cr2O7, which is a bright orange compound that we can reduce to the blue-violet solution of chromium cations. And under certain conditions, this can actually react with ethanol to form chromium 3+ and CO2. So this is the reaction equation. And your task is to balance this equation. And the first step is realizing what is actually oxidized here, what is reduced. So for the reduction, we have Cr2O7 to -2Cr3+. What are the oxidation numbers? So oxygen is always -2. So this is -14. Divided by 2, that is it's 7. But we have also 2 minus charge here, which means the chromium is not 7 but 6, right? And it's 6 times 2 is 12 minus 14, so it's exactly -2, right? So it's going from +6 to +3. And then the oxidation half reaction is ethanol to CO2. The carbon is getting oxidized here. Remember, oxygen is -2, then it's -1, +5 is +4, divided by 2 is 2, so this must be 2, minus 2 to 4. Yeah, minus 2 to 4. Okay, so we have the first step always is you write down the oxidation numbers of each element. You realize what is getting oxidized and reduced, and then you have it. Okay, so now the next step. Next step is you balance the half-cell reactions. First, you balance actually the elements that are reduced or oxidized. They should be balanced first. So in this case, you have Cr2O7, so you need 2 chromium on the right side as well. For balancing out the oxygen number, you can then add water, because for water, the oxygen oxidation state will be the same in this case, right? So we can easily just add it here. So now it doesn't really matter what you do as a next step. You could also balance the electrons first and then the protons and then the water, or you can do the water first. I think both strategies will work. So I just follow this idea now that they do. So balance the atoms first. And then you realize that the left side has a 2 minus charge, but the right side has a 6 plus charge, right? That cannot be true because the charge should be the same. It should be conserved. So we can just add some protons here because protons are always found in acidic solutions. So you have then 14 protons plus 2 minus is 12 plus, right? And the right side is 6 plus, right? So how they did it here is they actually, okay, I understand the conceptual idea. They have a different idea than me. So their idea is we just balance first the oxygen with water and then the hydrogen with protons, right? You can do it like that, or you can just focus on the electrons and charges first and then on the atoms, which is what I usually do. Okay, and then they balance the charge using electrons so that the total charge on both sides is the same. Okay, and then for the other reaction, ethanol to CO2, so again they balance the carbon first, which is getting oxidized. So you have 2 CO2 on the right side. Then you balance the oxygen with water. You add 3 water, then you have 4 oxygen on both sides. And you balance the hydrogen using H+. Now you have exactly 12 hydrogen on both sides. And then you add the extra electrons here. Wait, something is weird, right? It's not 12. 6 hydrogen, 7 hydrogen. No, it's 12. It's 6 plus 6 is 12. Yeah, and then you balance the charge with the 12 electrons. Yeah. Okay, so maybe I write you my way one more time because I really like that more. So sorry for that, but I really prefer to balance the electrons first because the electrons should be matched with the oxidation numbers. So my way of doing this would be like this. So we have ethanol reacts to 2CO2. Then you write down the oxidation numbers. This was 4 here. And this was, what was it, minus 2 or, let me see, to write this one. 4, minus 2, right? Minus 2. So what I would do now is I would see how many electrons were actually lost from minus 2 to 4, right? That's 6 electrons, right? But since you have 2 carbon, it would be 12 electrons. So we have to add 12 electrons here. And then I would do the next step. And I would say, okay, now I have the 12 electrons, but now the right side has 12 negative charge. I don't like that, so I add 12 protons here. And then in the last step, I would go and say, okay, now I need to balance my number of electrons. And since I always have water lying around there, I just add some water there, so it's 12 hydrogen here. So I need 6 water. Right? So I would do it in this direction. So this would be the third step. This would be the second step. And where's my red? This would be the first step. Now, if you get the right result, I don't mind, right, which direction you follow, but I usually prefer this direction. Okay. So we ended up with that equation here. And now we have the half reactions, right? And now we just need to see how many electrons do we produce in one of the half reactions versus how many do we actually use up in the other one. And they have to match each other, right? Because ultimately the reactions happen not separately, they are connected to each other and they use the same electrons. So we multiply the reduction half reaction by 2, then we also have here 12 electrons, just as we have it here. And now we can add up these equations together. So we just write them here. This is the first one, and the second one, the oxidation reaction. And then we just add them up. Then we have here 12 electrons, but there also we have 12 electrons, so they cancel out. We have ethanol here, we have 2 chromate here, and we have 16 hydrogen. Why 16? We have 28 minus 12 is 16. So 16 are left here. And then on the other side, we have 4 of these chromium cations, 11 water, 14 minus 3 is 11, and then 2 CO2. Okay, so you just add up these 2 equations together. And then in the end, you can check one more time if all the elements and charges are balanced, which now should be true because you balanced everything carefully. Okay? So if you are not in the acidic solution but in the basic solution, then usually you would balance the equation not with protons but with hydroxide, OH minus, right? So that's why I also like this strategy more. It's a bit logical. You focus on the electrons first, then the charges, and then the atoms. So instead of protons, you can just balance this with hydroxide on the other side, right? OH minus. It will be the same idea then. After that, it's the same as with the protons. Okay, so let's do one more example. Silver, sometimes found in nature as large nuggets. More often it's found mixed with other metals and arrows. An aqueous solution containing cyanide ion is often used to extract the silver using this reaction, which occurs in basic solution. We have silver reacting with cyanide and oxygen to form silver cyanide. So we need to first figure out what is getting oxidized, what is getting reduced. What is getting oxidized here? What's your guess? Any guess what is getting oxidized? Silver, I see some moving mouth depicting silver. Silver is going from oxidation state 0 to, what is this actually? This is minus 2, right? So it's silver plus. Okay, so it's going from 0 to plus 1. So if silver is getting oxidized, what is getting reduced? Oxygen. Oxygen is getting reduced. Oxygen is a strong oxidant. That also means that it can be easily reduced to water. Right? Okay, so we have already some idea here what happens. So we can write down the reactions here. Okay, so yeah, as always, they follow a little bit different strategy. I would do it the other way around. I would add the electrons first, but in this case, it's pretty straightforward. So you just need to balance. You have 2 cyanide there, so you also need 2 cyanide there. So you will need first the balanced number of carbon, and then just the number of electrons are added, and since already all the atom balances are satisfied, you're already done. For the reduction, you have O2, water, right? Water, oxygen is getting reduced to water naturally. And then you could do it in the 2 ways again. You could use my way and balance the electrons first, or you could use their way and balance the hydrogen first, and then the electrons. So ultimately you reduce oxygen to water from oxidation state 0 to -2. And then you multiply this equation so that you have the same number of electrons. Now you have 4 electrons in both equations. You add them up together and you get the final equation, chemical equation for the reaction. Yeah, so I really recommend you to practice this sometimes, like until the short test, next short test, so that you know, you feel confident with balancing those equations. Yeah. Okay. So this was in the acid, and now if you would be in alkaline conditions, then you could simply replace the protons. So how they suggest it is you just add the equal amount of hydroxide here, and you form water, right? Hydroxide plus proton is water. So you can form 4 water molecules, and then you have 4 hydroxide remaining. And that's how you can easily get the same equation as in the, you can get the equation for alkaline conditions. And then you eliminate the remaining water. Okay, so how they recommend it is to write down the equation first with the protons and then convert it eventually by adding hydroxide. What I recommend you is to just do this strategy, and it's very easy. So if you stay with this example here, right? So the first thing is, again, you add the electrons. It's 12 electrons still. And the second step is you want to balance the charge. Since you have 12 electrons here, you would add 12 OH minus here. That's the second step. And then in the third step, you would simply then balance the water, the oxygen and the hydrogen atoms. So here you have 1 oxygen plus 12 is 13 oxygen atoms, right? And here you have 4, so 13 minus 4 is 9, right? So you need 9 H2O. And you can see if it's okay, so it's 18 hydrogen here, and it's 12 plus 6 is 18, right? So hydrogen is satisfied as well. So this is the strategy which I recommend you, and you don't need to do anything weird anymore. Just always do first the electrons, then the charges, then the atoms. It should all work out. Okay. Any questions to this? No? I would be also really surprised if a question would come in the class. Be shocked. Yeah. Okay. Now oxidation reduction reactions, as all reactions, they can be quantitative, meaning they can convert all the reactant to the product, or they cannot, right? But if they are quantitative, meaning we convert all the reactant to the product, then we can use them for titration, right? If you remember, for titration we prefer reactions which are complete, right? Which convert all the reactant to the product. So we would probably use something here, some very strongly oxidizing agent, so that the redox reaction is converting all the reactant to the product. So examples here are potassium permanganate, potassium dichromate, serum hydrogen sulfate, for example, right? Oh, what happened there? This should be small s here, right? Hydrogen sulfate, large s, large s. So these are typical oxidants. So if you have something you want to determine, and then you just titrate it, you oxidize it, and then you determine by that the concentration. Permanganate has an advantage. It's actually also its own indicator. So permanganate is intensely purple, and the manganese is almost colorless. Yeah. And it's actually not so good to get into contact with that one, which I experienced by myself in the lab course. Okay, anyways, so the solution remains colorless as long as some reducing agent remains in the solution being titrated. So you can basically drop this into the solution, and then once you see this turning purple, you know that the reaction has been complete. Okay, that's the idea. So you can solve these problems then exactly like the acid-base titration, right? So you formulate the reaction for the redox reaction, and then you use the stoichiometric coefficients to determine the equivalence point where N of the oxidizing species and N reducing is the same. C oxidizing times volume oxidizing is C reducing. Then you can determine this concentration by just measuring how much oxidant you needed and how much reducing volume you prepared, and concentration of your oxidizing solution, right? So that's the basic idea here. Okay, so then let's move on to the next lecture. Still have a bit of time. Did I already share this? Maybe not. Not yet. Okay, so we will have a really rough breaking point now. As I announced to you in the very beginning of the semester, this book is not too much interested in the slow transition between topics. So we will talk about gases this lecture now. So essentially this lecture will be about physics of gases. And this will be needed so that we can better understand what happens to gases when we, for example, increase conditions like temperature, pressure. Well, how does that influence chemical reactions and so on? Yeah. So so far we talked about solution reactions. We want to now transition to gas reactions, which are actually easier, and it allows us to give us some kind of microscopic understanding what happens during reactions. So we usually have like two atoms meeting together and making a reaction and so on. Okay, so for that we have to define a couple of physical properties like pressure. We have to talk about gas stoichiometry, and then we talk about the kinetic molecular theory of gases. So how fast are these atoms moving? What actually is needed to make them react to each other? Okay. So if you remind yourself what I told you before about gases have a property that they have not a fixed volume, right? For all these liquids, we always talked about the volume. For gases, they will just adapt to the container in which they are in, right? And they are also easily compressible. We can use force to reduce their volume more. And they will mix with other gases completely, not like solutions where we usually have precipitation happening. And they exert a certain pressure on its surroundings. This is just an example here of pressure exerted by the gases in the atmosphere. Well, this is heating up this container, which leads to gas going out, and then I think the pressure of the environment becomes larger and will compress this thing. But maybe if you flew in the airplane, then you have experienced it by yourself, that your water bottle has shrunk like suddenly, right? So it has to do something with pressure inside and outside the bottle. So gases can exert pressures on dividing walls, right? So one thing that we have to know when we talk about gases is definitely pressure and how to measure pressure. What is actually the pressure? So pressure is just the force per area. So we will realize during this lecture that pressure has to do with molecules hitting a surface and exerting a certain amount of force on them. So this is what we will find out during the lecture. So these molecules are moving around, they hit the surface, and then they exert a force on this container. This is what essentially pressure is. So how can we measure that kind of pressure? So if we have atmospheric pressure, right, that actually results from the air being pulled to the center of Earth, so this is the Earth here, then we always have this block of air until the end of the atmosphere. This would be the atmosphere. And well, this will exert a certain pressure on the ground, so because this is dragged by the gravity to the center of Earth, right? So gravity will kind of pull these molecules down, the air molecules, and that will lead to a certain pressure that is exerted by these molecules. Yeah, and this is usually called the atmospheric pressure, which strongly depends on the weather condition and also how high you are, right? If you are on a mountain here, then this volume of gas is much less, right? So the pressure here would be very low, and the pressure here would be very high. Then this exerts on the ground, right? And so how can you measure this one? Well, if you think about you have a glass tube and you fill this with a liquid and then you invert it in a dish of mercury. Okay, sounds weird, but this is how this looks like. So you have mercury, which is a liquid metal, so it has a very high viscosity. You have this here, and then you have this long tube. And now what happens? The atmospheric pressure is pressing from the top, right? This is the force this column of air is exerting on the ground because gravity pulls the air down. And this will actually push up the mercury inside, up the column, right? So you can imagine that depending on how long this mercury is going up the column, you can understand about the pressure of the environment, right? So if this thing would be down here, would the pressure be high or small? If this column here would be down here, is it high or small pressure? Who thinks it's small? Who thinks it's high? So it's actually small because you can imagine this pulling up the liquid outside, right? It's not pressing it too much, then this thing inside can come down. If the pressure outside is high, it will press this down and up, and the inner column will move up, right? So we can measure this length here of the column, and the longer it is, the higher the pressure. Yeah? And we will usually normalize this so that the atmospheric pressure will give us exactly 760 millimeter of mercury going up the column for a standard atmosphere. So this is how people then shows the thickness of this tube. And then basically you can go with this thing, you can take it up the mountain, and you will realize that this thing goes down because the pressure is less. This is, by the way, called Torricellian barometer. That's why the unit of pressure is called torr. So this is the atmospheric pressure has a value of 760 torr. Yeah. Okay. Then we can also use this device not only to measure atmospheric pressure, but we can modify it a bit to measure the pressure of a gas inside a container. Yeah. So in this case, we would do it like this. This is called a manometer. So we have here this enclosed gas, and it's enclosed by the mercury. And now you can again imagine that the inside gas will press this mercury out. But from the other side, you have the atmospheric pressure, which is pressuring in the other direction, right? So you have a force balance between the two, right? And depending on how high the pressure inside is, relative to the atmospheric pressure, this height here will change. So you can say that the gas pressure equals the atmospheric pressure minus the height, where you measure the pressures again in terms of millimeter of the displacement. So if the height is 0, that means the pressures will be exactly the same. If the height is, in this case, negative, right, then P gas would be higher than P atmosphere. But actually, in this case, P gas is smaller than P atmosphere. So I guess they define the height in the other direction. So I guess this would be a positive height and this would be a negative height. So no, sorry, wait, 1 second. Okay, so they just put minus h here. So h doesn't have any sign, so they just put h here. So this is P gas is P atmosphere minus h because this is displaced in this direction, and here's displaced in the other direction. That's why you have a plus here, right? So you can measure with this manometer, you can quantify the pressure of your gas by referencing it to the atmospheric pressure. So what are the units of pressure that we should use? So I already told you we have the torr unit, right? 760 millimeter of mercury, we call this 760 torr. That's 1 atmosphere. That's the atmospheric pressure. So we also often call this 1 standard atmosphere, 1 ATM. Okay? So these are units we can use. But there are also other units we can use. So for example, we can move over to the SI unit of pressure. Since pressure is the force over the area, and the force is measured in Newton and the area in square meter. So if we use these kind of units, then we would get a different value out. And we define this unit as Pascal. So Pascal is 1 Newton per square meter. So 1 atmosphere corresponds to 101,325 Pascal. Yeah? And 1 atmosphere, so it's roughly 10 to the power 5 Pascal, right? Okay, so the Pascal unit is not super useful if we want to talk about atmospheric pressure, because typically we deal with pressures which are so high in Pascal units, right? So we usually want to avoid talking about 10 to the power 5. So that means we prefer talking about atmospheres usually. But Pascal is the SI unit, so whenever you do any calculations with pressure, you should use Pascal. Yeah, that's the important thing for you. So we cannot ignore Pascal because it's the SI unit. So whatever you calculate, use Pascal. But then when you think about the actual value, it makes sense to use atmospheres. Okay, so one example here, the pressure of a gas is measured as 49 torr. Represent this pressure in both atmospheres and pascals. Okay, so how do we do this? 49 torr, we know that 1 atmosphere is 760 torr. So we can multiply it with this factor, the torr cancels out, and we get 6.4 times 10 to the power minus 2 atmosphere. Okay. And in Pascal, we use the conversion factor between Pascal and atmosphere is 10 to the power 5 roughly Pascal per atmosphere. So we again shorten this and get the result. Now, we know a little bit about pressure now. How about volume, right? Volume and pressure should have some kind of relationship. And that is what Robert Boyle already realized many decades ago, centuries ago actually. And he found some relationship. So, because with this manometer device, you can simply try to induce a different pressure from the outside. And then you can modulate the inside pressure and the inside volume, right? So you can get a relationship between pressure and volume. And what he found is that multiplying the pressure and the volume, you always get a constant. So let's say you double the pressure, then the volume will always be half of what it was before. Yeah, and K seems to be a constant, which for a given sample of air, which only depends on the temperature. Yeah, apparently. Okay, so this is what he realized with many experiments, and this was basically the experiment he did to get this equation. So he used again this kind of tube where you have the gas inside and the atmospheric pressure outside. And then he modulated the pressure here by adding more mercury. So he could reduce the volume of the gas, and he can still measure the pressure of the, that corresponds to this height, right? So with this device, he could get the relation between pressure and volume like this. And you can see while the pressure is decreasing, the volume keeps increasing, right? And the product of these two is always the same. So this is now called Boyle's law. And you can represent that result using different ways. So you could, so you could plot P versus V. So P times V is a constant K, so which means P is K over V, right? So if you plot P over the volume, then you get a hyperbolic relationship. That's one way you could do this, but you could also say, okay, let's plot P versus 1 over the volume, then you get a simple straight line, right? So it seems that this kind of plot would be a little bit more easy, because we can directly see the slope here as the coefficient K, right? These are the different ways that we can draw this one. Okay, so we just convert this into a linear equation by plotting versus 1 over volume or 1 over the pressure. So these are these two different plots, P versus volume, which is a hyperbolic curve, and then volume volume versus 1 over pressure, or pressure versus 1 over volume, which gives you a straight line with the slope of k. Okay, now what they also realize, what Boyle also realized, is that apparently this Boyle's law is not valid always. Yeah, there are exceptions, especially when you increase the pressure more and more. Yeah, when you increase the pressure more and more, then you start seeing deviations from this straight line. Yeah. So apparently there's a limiting case where the pressure goes to 0, where Boyle's law is valid. Now if you think about it, right, what does it mean pressure goes to 0? It means the volume will just keep increasing, right? So the particles inside the gas, they are getting more and more distant from each other. And they move essentially independently from each other through the cylinder, through the container, right? And this is what we usually call an ideal gas. So an ideal gas means that the molecules or atoms, they are not interacting with each other. They just behave as if they were be completely alone. And in this limit, Boyle's law is perfectly valid. But once you keep increasing the pressure, what happens? Well, then these atoms will start colliding with each other. They will start interacting. So they realize that there are other atoms around it, and that changes this curve. Okay, so you can see here that if you go onto 1 atmosphere, everything looks pretty much ideal only at the very low pressures. So what they plot here is P times V. So there should be a constant, it should be like the dash curve. But you can see already at like half an atmosphere, you already start get deviations from the ideal gas, especially for something like CO2. Like for neon and oxygen, you could say they behave ideal under atmospheric conditions, right? Which is a relief, because we have this very simple relationship between pressure and volume. We would like to use it in practice. It would be completely worthless if it would break down already for oxygen, right? But luckily it doesn't. But when we use something like CO2, we already get some deviations. To be honest, the deviations are still not super large, right? We are talking about, 5% error or something like that, or even less. So still, even for CO2 at atmospheric pressure, we could probably use that ideal gas relationship. So that's really good for us. So we should just be careful that when we go to too high pressures, that then we do need to correct somehow this relationship. Okay, so let's do one example here. We consider sulfur dioxide, SO2, which is a gas that plays a central role in the formation of acid rain, because it's found in the exhaust of many automobiles and power plants. And we consider a 1.53 liter sample of gaseous SO2 at a pressure of 5.6 times 10 to the power of 3 Pascal. Okay, volume is given, pressure is given. Now the question is, when you change the pressure to something higher, and you fix the temperature, what will be the new volume? And that's straightforward with Boyle's law, right? We know the initial pressure and the initial volume, and we know the final pressure. So we just need to solve Boyle's law here, right? P1 times V1 equals P2 times V2, because P times V is a constant, right? So it doesn't matter what happened from beginning to end. The product of these two has to be the same. So we just solve for V2. We get V2 is P1 V1 over P2. And we insert everything with the units, and we get 0.57 liter. It is smaller than before because the pressure increased, so you did everything correctly. Okay. You can do this exercise for you as a practice. Now one more. Okay, so this is one more example. So we have gaseous ammonia, and we want to see how closely it resembles Boyle's law. So essentially, how ideal is ammonia, right? We measure different pressures using a fixed number of ammonia particles at a given temperature. And then using the results that we got from experiment, we want to calculate Boyle's law constant, and we want to see if it is ideal or not. Okay, so this is the experiment. So 6 different experiments, 6 different pressures and volumes. And now the question is, how ideal does ammonia behave? So we simply just modify the 2 and get the K. K is P times V. And you can see it's pretty much ideal, but it does introduce an error, right? So if we, okay. I think there's also the plot here. So this is the plot of P times V versus pressure. And you can see that at 1 atmosphere, we already introduced deviations from the reality, right? Still, it's relatively small percentage-wise, but it is something that can make some errors in your calculations, right? If you use the ideal gas law. And what you can now do with this is you can actually extrapolate also the K value, because you can see that K is roughly linear with the pressure. So you can extrapolate this here to the value of 0 pressure. Then you can get the value for K for an ideal gas. And that would be now 22.41 liter atmosphere. Okay, and this is apparently exactly the same value as for other gases. So it turns out, because let me show you this one again. Turns out that all these gases kind of have the same value of K, right? You see this here. They all converge to the same value of K. So it seems like when the gases become ideal, it doesn't matter anymore what gas you have. They all behave exactly the same. Yeah? They have exactly the same relationship. Okay, and then one thing, however, is left is the temperature, right? The temperature, we set it to a constant before. So there was a French physicist, Jacques Charles, and he actually found that the volume of a gas at constant pressure increases linearly with the temperature of the gas. So what he actually did is he set the pressure constant and then observed the volume-temperature relationship. Okay, so if you plot the volume versus the temperature, it gives you a straight line. Like this one. Okay. And well, the question would be actually about the unit of the temperature, right? We introduced degrees Celsius, right? And apparently it doesn't make sense that you have negative volumes, right? What would be the meaning of a negative volume, right? So we could say, okay, the point where the volume becomes negative, this should be the lowest possible temperature. So this would be 273 degrees Celsius. And since it makes sense to define this as a new 0 point, we call this 0 Kelvin. Yeah. So this is the unit Kelvin. Kelvin is introduced based on the idea that, well, the volume should always be a positive number. So when the volume is 0, this is the point we can never reach exactly. This is the lowest possible temperature for an ideal gas. Yeah. So this is how this looks like. So you have like all these different measurements of volume and temperature relation. They are proportional to each other with different slopes depending on the gas, and then somehow they all reach the same point where the volume is exactly 0 and the temperature is minus 273, which is defined as 0 Kelvin. This is the lowest volume that you can have. Okay. Okay, so Charles' law, we can summarize it like this. Volume is proportional to temperature, and we have some kind of constant there, which we call B, proportionality constant. Okay, and now we do one more example for this as well. So we have a sample of a gas at 15 degrees and 1 atmosphere, given volume, and we should determine the volume at 38 degrees Celsius and 1 atmosphere. So we have to use this, we have to write down all these equations. We first convert degrees Celsius to Kelvin, because it turns out that Kelvin is the SI unit. So you should always use Kelvin and Pascal. Yeah? So 15 degrees Celsius plus 273 is 288 Kelvin. And 38 degrees Celsius plus 273 is 311 Kelvin. So this is the temperatures you should use. And the volume is 2.48 liter in the beginning. Then you again use this relationship. In this case, the volume over the temperature is a constant. So you set the volume over temperature before equals volume over temperature after. Then you solve it for the volume 2, which gives you T2 over T1 times V1 units Kelvin crossed out, and you get 2.79 liter. Does it make sense? Well, the temperature increased, so the volume should increase, right? Makes sense. Okay, now one thing we have ignored so far. So we have now the temperature, volume, and the pressure, but we never talked about the number of particles. Now, if you think about it, there should be a relationship, right? Because having more particles would probably mean a larger volume, right? Because both of them are extensive properties. So if you double the system size, both of them should double, right? And that is what Avogadro also realized, an Italian chemist. And he postulated that the volume is proportional to the number of moles of particles, or the particle numbers. And there's another proportionality constant there. So for a gas at constant pressure and temperature, the volume will be directly proportional to the number of moles, right? So you can, and that also means actually that when you have different gases and they have same number of particles, they will always have the same volume. It doesn't matter if you have a neon balloon or you have an argon balloon or a methane balloon. Well, as long as we have the same number of particles or moles in there, they will exactly have the same volume. Again, this assumes an ideal gas, right? Why? Because once you increase the pressure, these molecules start interacting, and they realize, no, this is not a neon, this is methane, or they start to realize what other molecules are around them, right? And then this will change. But Avogadro's law again holds for ideal gases, like all the other laws that we have. So suppose we have a 12.2 liter sample containing 0.5 mole of O2 at a pressure of 1 atmosphere and temperature of 25 degrees. If all this O2 were converted to ozone at the same temperature and pressure, what would be the volume of ozone? So for this, we have a chemical reaction. So we should write down also the chemical equation. First, we write down everything we have. We know the initial mole number of O2. We know the volume. We don't know the final volume of the product. And we also don't know the initial number of O3. So what information do we need? Well, we first need a balance equation. We need the moles of O3, and then we need Avogadro's law to convert it to a volume. So how do we do this? First, we realize how many moles of O3 we produce from the 0.5 mole of O2. So for this, we write down the balance equation. So we have 3 O2 reacting to 2 O3. That means that the mole ratio will be 2/3, right? So we will produce 2 ozone molecules per 3 oxygen molecules. So since we have 0.5 mole of oxygen, that means we will produce 0.5 times 2/3 of O3, which is 0.33 mole. And then what will be the volume of O3 produced? Well, we just use Avogadro's law now. The volume over the mole number should be same, right? Should be constant. So we can also write it like this: volume over mole number before and after should be the same. So V1 would be now the volume of N1 moles of O2 gas, while V2 is the volume of N2 moles of ozone gas, right? We converted all the O2 to the O3. So we have initially we had 0.5 mole of O2. Now we have 0.33 mole of ozone. Remember, the molecule doesn't matter for this, right? Because we are in the ideal gas limit. So all these equations hold independent of if we have ozone or O2. It's an ideal gas, right? It doesn't matter what gas we have. And we knew before we had 12 liters, so we can just solve this for V2. V2 is then N2 over N1 times V1. We just insert our mole numbers there and the volume, and we get 8.1 liter. So what we realize is that the volume has decreased now, which is simply because we have less moles of ozone formed, because O2 molecules combine to form less ozone molecules than before, so the volume has to decrease, right? So if you have chemical reactions in which molecules form larger molecules, that will typically mean that the volume has to decrease, right, in the gas phase. Okay, you can do one more exercise for this. Let's do some join-in here. A balloon contains a certain mass of neon gas. The temperature is kept constant, and the same mass of argon gas is added to the balloon. Okay. Let me make some space. Okay, so we have a balloon here, pretty balloon. We have some neon gas in here, which has a certain mass, and the temperature is constant. And then we add the same mass of argon gas. What happens? A, the balloon doubles in volume. B, the volume of the balloon expands by more than 2 times. C, the volume of the balloon expands by less than 2 times. D, the balloon stays the same, but the pressure increases, or E, none of them. Thinks it's A, B, C, D, E. It would be funny if it would be E, right? At some point. Like, I don't know why they ever always put this answer there. Okay, so what do we know? We know Avogadro's law, right? We know that because all of these answers talk about the volume, right? So we should consider that particle number is proportional to the volume. That's definitely important, right? But they're not talking about particle numbers, they're talking about mass, right? So we need another relation, which is n equals m over m. So the mole number is actually related to the mass directly, but via the molar mass, right? Now argon and neon, they have different molar masses. Argon has approximately double the molar mass of neon. Okay, and that means for the mole number of argon, this will be the mass over the molar mass of argon, which is 2 times molar mass of neon, right? So this will equal 1/2 the mole number of neon, right? So adding the argon to that, we will now add not the same amount of particles, but less than only half of these particles. We add more to this, right? And since the particle number directly relates to the volume, this means the volume cannot double. It cannot fully double because that would mean that we add exactly the same number of particles again, which we don't, it's only half, right? So A cannot be right. B is the volume of the balloon expands by more than 2 times. That's also not possible because that would mean that the molar number should be larger than the molar number of neon, right? Then ultimately we would end up with more than double. And C is apparently the right answer because we will eventually end up with roughly 1.5 the amount of volume that we had before. Okay, each of the balloons holds 1 liter of different gases. All 4 are at 25 degrees and each contains the same number of molecules. Of the following, which would have to be the same for each balloon? I'll just show you this one more time, right? Okay, same temperature, same number of molecules. What has to be the same? A, densities. B, masses. C, buoyancies. D, the pressures. Okay, so we said that the number of molecules is same. If the number of and the volume is also same, right? So if the volume is same and the temperature is same, the pressure has to be also same, right? So that is what needs to be constant here. A cylinder is fitted with a movable piston. The pressure inside the cylinder is Pi. The volume is Vi. What is the new pressure in the system when the piston decreases the volume of the cylinder by half? So this goes to this situation here. What is the new pressure? Oh, this is Pi over 2. Who thinks it's A? 1/4, 1/2. 2 times, 4 times, none of these. No, just joking. it should be double, right? Volume has half, so the pressure should be double. And now we can actually go ahead and we can write all these rules down one more time. So, pressure and volume is a constant. The volume is proportional to the temperature. And also the particle number is proportional to the volume. And now we can actually combine all these equations together in a single expression. All of these expressions are exactly satisfying this rule. This is called the ideal gas law. Now this is actually more powerful because for these expressions we always assumed a constant, right? Here T and N is constant. Here the pressure and N was constant. And here the pressure and the temperature is constant, right? So these were kind of like some specialized cases where we keep some of these variables constant. This is the general law when you actually can vary some of them at the same time. You can vary, so it's more general. It contains much more information than these. But it turns out this is actually true also in reality. So we have like one beautiful equation that enables us to always calculate the relationships of these four variables: the pressure, the volume, the mole number, and the temperature. So once you fix 3, then it gives you the remaining one. Okay? So next time we do a couple of examples for this. Okay? Thank you.